How do you quantify a linear statistical relationship between two variables? This video gives a visual and intuitive introduction to covariance, one of the ways we measure a linear statistical relationship. Covariance values above zero mean positive linear relationship. Negative covariance values indicate negative linear relationships. And covariance values close to zero indicate no linear relationship between two variables. Here's a scatter plot. On the horizontal axis is the living area of residential homes that are for sale. And on the vertical axis is their sale price. The point in yellow right at the center of the scatter plot represents a home with an average living area and an average sale price. So the question is, do homes with larger than average size or larger than average living area tend to sell for higher than average prices? That is actually the case in this example. With the exception of a few homes, dots to the right of the dashed vertical yellow line have above average sale prices, above the dashed horizontal yellow line. Okay. Similarly, homes with smaller than average living areas on the left here tend to have less than average sale price. By visual inspection, we see these two variables directly covary together, positively covary together. The covariance between them is going to be positive. So, how do we numerically quantify their statistical relationship with covariance? Let's start by looking at some specific data points. All right, let's take a stride to the top right from the center. And we have a point that has a living area larger than the average home by 462 square feet. Its sale price is also higher than the average home by about $59,500 US. All right, here is another example. Its living area is actually 901 square feet less than the average home. And we write negative 901 to signify that it has smaller than average living area. The sale price of this home is also lower than the average sale price by about $91,800. A reduction in sale price, which we represent as a negative number. So we see a reduction in living area that is met by a reduction in sale price from the average. All right, based on these two sample points, we see that living area and sale price have a positive relationship. They covary in the same direction. Okay, now multiplying the change in one variable and the associated change in the other variable could give us an indication of how these two variables covary. So multiplying the increase in one variable by an increase in the other variable gives a positive value. We also get a positive product if a decrease in one variable is met by or is associated with a decrease in the second variable. However, if an increase in one variable is associated with a decrease in another variable, we would have such a product being negative. Positive product indicates two variables moving in tandem in the same direction, while negative product indicates the two variables moving linearly in opposite directions. Okay, let's go through the rest of the data points in our sample. Here is an example home for which an increase in living area is associated with a decrease in sale price. The product of the deviation from the mean of the two variables, from the means of the two variables, is negative. So for most of the data points in our sample, an increase in living area, an increase in the x variable from the average is associated with higher than average sale price, an increase in the y variable and the vertical axis variable. And a decrease in living area from the average is associated with lower than average sale price. But there are a few exceptions, just like the one we have just seen. Each point in our sample contributes to how the two variables tend to covary. Most data points tell us these two variables tend to change in tandem in the same direction, linearly. However, the influence of the few exceptions we have seen is largely compensated by the rest. So how do we combine these individual contributions, individual observations of how variables covary into one overall measure of covariance? One approach is to sort of average out these individual data points' tendency to covary into sort of an average tendency to covary. Well, that is the idea behind covariance. The products of deviations from their means are averaged to give what we call the covariance. Actually, since we have spent 1 degree of freedom calculating the mean values, we sum the products of deviations from the means and then divide by the number of observations minus 1 instead of dividing by the number of observations in our sample. This is how you calculate covariance from a sample that has n observations. In general, if we have two random variables x and y, which have population means of the expected value of x and expected value of y, their covariance, denoted by COV covariance x, y, is the expected value of the product of deviations from the means. The expected value on the outside takes the role of the averaging we just saw in the example. Let's look at another example really quickly. We still have the sale price of a home on the vertical axis, but now we have the age of a home on the horizontal axis. Older homes are on the right side of the scatter plot and newly built homes are on the left. Visually, you can see that older homes tend to have associated lower sale prices and newer homes tend to be more expensive. That makes sense, right? If you think of having a linear line fit to the data, the slope of the straight line would be negative, right? The covariance between age of homes and their sale price is also going to be negative. So older than average homes typically have lower than average sale prices, and newer than average homes tend to have higher than average sale prices. Summing up the products of deviations from the sample means and dividing by the number of observations minus 1, we get a covariance based on the sample data. And it is negative, signifying a negative linear relationship between how old a residential home is and its sale price. All right, let me give you a couple more thoughts and then I'll close out this video. Covariance only measures linear relationship. Here's an example. The variable x on the horizontal axis is non-linearly related to the variable y on the vertical axis. So the green curve shows the non-linear relationship between the two, and I used that to generate the data. Now let's forget about that green line. Due to the nature of the nonlinear relationship between the two variables, the linear line that fits the data has a slope that is very close to 0. It's almost a horizontal line. Similarly, when we calculate the covariance based on this sample data, we get a value that is very close to 0, showing almost no linear relationship between the two variables. So the point I want to make here is that covariance only measures linear relationships. Two random variables, so two variables can have nonlinear relationships, and covariance may not measure that. Covariance as a measure of relationship is not one of the best ones. It has its drawbacks. For instance, if we had recorded the living area of a home in square meters instead of square feet, the value of the covariance from the same sample of homes would be different. Here's another drawback. The covariance between two variables is not meaningfully comparable to the covariance of two completely different variables. I cannot meaningfully compare the covariance between the sale price of a home and living area and the covariance between, let's say, the stock price of Apple and the stock price of Microsoft over time. Therefore, it makes it hard to attach meaning to the number that you get out of covariance. It is also not bounded from above or from below. It could take values from negative infinity to positive infinity. So instead of covariance, it is typical to use the product moment correlation coefficient to express linear statistical relationships between two variables. I hope you enjoyed this video. If you stayed this far into the video, I appreciate you spending your time here. So thank you. Don't forget to subscribe to this channel and share with your friends who you think would benefit from this.